Good morning, everyone. My name is Muhammad Al Hayat, and I am presenting our work on Phase-Derived Temporal Fingerprints for cross-domain detection of cyber and physical attacks in power networks. This is joint work with my colleague, my supervisor, Dr. Muhammad Al Hubayshi from the Department of Computer Engineering at Haliç University in Istanbul, Turkey. Today, I will show you how we developed an advanced detection framework using physically grounded VHR engineering to identify sophisticated attacks on smart grid infrastructure. Here is our roadmap for today. I'll start with the motivation and problem statement, then walk you through our proposed PTTF methodology and system architecture. We will dive into our experimental setup using a large-scale data set with over 1.2 million records, examine our cross-validation results, and discuss VHR importance and explainability. Finally, I will present our application study results and conclude with future directions. Let me start why this problem matters. Modern power grids face an expanding attack surface due to the growing interdependence between information networks and electrical infrastructure. This creates vulnerability to coordinated cyber and physical threats. The detection challenge is significant. Malicious actions manifest as subtle, temporally correlated perturbations in VHR signals that are easily confused with legitimate operational variability, things like normal load change or switching events. Most critically, we identified a cross-domain impact problem, single-domain measurements, looking only at network logs or only at electrical signals, risk missing cross-domain causal chains. This produces overly optimistic evaluations due to information leakage. Our work addresses all three of these challenges. Let me be more specific about the technical challenge. First, attacks produce coordinated perturbations across multiple phase measurements that are difficult to distinguish from normal operational noise. Second, relying on network logs or single-domain measurements alone risks missing cross-domain causal chains. An attacker may manipulate network traffic to mask electrical anomalies. Third, we found significant information leakage in existing evaluation protocols, spurious performance due to temporal or device-level leakage. Fourth, models must generalize across heterogeneous PMU deployments without retraining for each device. Fifth, detection must remain robust under concept drift over time and varying operational conditions. Finally, security operators require explainable decisions to validate detections and refine response procedures. What is required in physically grounded VHRs that capture coordinated phase domain patterns while preventing information leakage and enabling interpretable cross-domain detection. That's why exactly what PTTF provides. Our work builds on three research streams. First, theoretical foundation from Pasquality and colleagues established observability constraints and detectability limits, motivating multi-signal anomaly detection. However, this provides limited practical implementation guidance. Second, spatio-temporal methods like temporal topological calculation and graph-based detection showed promise, but they required extensive topology priors and show limited gross domain generalization. Third, deep learning approach using RNNs and GAN and time frequency methods achieved good performance but suffer from limited interpretability, required large labeled data set, and don't explicitly model phase domain physics. Our contribution, Phase-Derived Temporal Fingerprints, provides compact, physically interpretable features including peer-phase, statics, inter-phase relationships, and temporal dynamics with rigorous cross-domain validation and explainability. This bridge with a gap between theoretical foundation and practical deployment. Now, let me explain our BDTF methodology. The design philosophy is to capture coordinated deviations across phases while reducing sensitivity to routine noise and nominal load change through physically informed temporal windowing. We use a window configuration of 128 samples without temporal lags at 1, 3, and 5 samples, and rolling windows of 3, 5, and 11 samples. Our VHRs fall into 5 categories. First, peer-phase statics, mean, standard deviation, minimum and maximum, and range for voltage and current on all 3 phases. Second, interphase relationships, pairwise angle differences with curricular statics, capturing phase imbalances. Third, short lag derivatives, vanity, the differences at multiple lags aggregated by mean and standard deviation and capturing rapid transitions. Fourth, multi-scale rolling summaries, rolling aggregated at different time scales to capture both fast and slow dynamics. Finally, relative index, phase variations, and unbalance measures like voltage imbalance and power factor. All VHRs are interpretable and grounded in power system physics, which is critical for operator trust and regulatory compliance. Here is our end-to-end detection framework. Raw phaser data flows through PDTF, VHR engineering. Then we apply rigorous train and test splits to prevent leakage. We use a hybrid detection approach combining multi-class gradient posting with one versus race binary detectors for improved recall on difficult classes. Finally, we provide comprehensive evaluation and explainability through confusion matrix, shape analysis, and permutation importance. This entire pipeline is reproducible and designed for operational deployment. VHR hygiene and leakage mitigation were critical to our work. We tested 3 experimental variants. First, with identity includes all metadata for diagnostic purposes. For no identity, removes device and capture fields to prevent spurious correlations. and no identity improved at physics-informed aggregation and pruning. Our VHR pruning strategy removes VHRs with correlations above 0.95 to eliminate multicollinearity and drop zero variance VHRs and eliminates capture metadata based on permission importance. The validation outcomes are interesting. Power VHRs show strong correlations at 0.88, but were retained for complementary aspects. Phase angle is orthogonal to power with correlation near zero. Validation, our cross-domain detection approach, voltage and current show moderate negative correlation at 0.47, confirming they provide independent signals. We found no perfect correlation except the diagonal, confirming successful pruning. The correlation heat map shows the relations between selected PDTF VHRs, demonstrating the independence of our phase domain VHRs. We used the Smart Grid Cyber Physical Attack dataset from IEEE Data Board, a publicly available dataset with approximately 1.2 million labeled records from multiple PLS and PMUS in a simulated ICS testbed. The dataset includes 6 attacks types plus benign, traffic, backdoor, brute force, and etc. Critically, we evaluated using 3 different splits to test different aspects of generalization. First, stratified split, random partition, specifying class propositions to measure within distribution performance. Second, time-based split, chronological split with aerial time stamps for training to test temporal drift and concept shift sensitivity. Third, group PLCID split, entire PLC devices withheld from training and reserved for testing to measure gross device generalization and eliminate device level leakage. This table shows the distribution across splits. Notes that in the time-based split, some attack types like backdoor appear only in training, while FDI and ransomware appear heavily in testing. This creates a realistic challenge for temporal generalization. The group-based split is the most challenging as the model must generalize to completely unseen devices. Let me show you our 5-volt gross validation performance using the with identity experiment. This represent upper bound performance with all VHRs. Gradient posting achieved 99.945% accuracy with an IUC score of 99.998, near perfect ROC performance. The micro FA scores was 0.958 with standard deviation of 0.058. Comparing across models, gradient postings significantly outperformed MLP, logistic regression, and extra trees and random forest and histochromer gradient posting across all metrics. To understand what drives detection, we used dual importance metrics. This chart shows the top 24 VHRs by gain, based importance, power domain VHRs, like reactive power and active power domain splitting decisions in the tree in sample. However, gain based importance can be misleading. The table below shows the permission importance, which measures if one score drop when a VHR is removed, revealing is a true impact on performance. When we exclude protocol metadata, based derived VHRs, current on phase C, voltage on phase B, and phase angle theta drive repose detection. This validates our design. Power VHRs provide coarse-grained class separation, but phase-derived VHR provide the fine-grained discriminative power needed for accurate attack detection. Understanding model decisions is critical for security operations. The shape summary plot shows the VHR importance for ransomware detection across 40,072 test instances. Phase angle theta domains with a shape value of 0.0742, making it the strongest discriminator at the ransomware class. Voltage magnitude on phase comes second at 0.0501, and frequency is third at 0.0311. This validates our PDDF design. Rational phase-derived VHRs provide the stronger discriminative power for attack-specific detection, while power domain VHRs provide coarse-grained class separations. Now, let me show you the impact of our leakage mitigation efforts. When we removed identity VHRs, the macro F1 score dropped from near perfect to 0.086. With our enhanced grouping strategy, we improved this to 0.218, and an improvement of 0.132 or 153.4%. This shows that mass prior work likely overstatement performance due to information leakage. For gross domain generalization, comparing stratified versus group-based splits, we see within distribution performance as 0.134, but device level holdout performance as 0.308. An improvement of 130%. This demonstrates that our BDTF VHR generalize better across unseen device than random splits would suggest. Our key research contributions are: first, phase-derived temporal fingerprints, compact domain-aware VHRs, including temporal and phase dynamics. Second, a hybrid detection architecture for targeted recall improvements. Third, rigorous gross domain validation with systematic leakage mitigation. And fourth, comprehensive explainability through shape and permission importance. Let me summarize our key conclusions. PDTFs offer compact interpretable descriptors that capture key perturbations in power systems. Metadata remover improved F1 by 153%, yielding a realistic performance estimates. Group-based splits improved generalization by 130% across unseen devices. Our hybrid detection approach posts recall for problematic stealthy attack classes. And shape analysis confirms that key features drive detection, providing transparency for operators. The framework is reproducible and ready for field validation. For future research, we are exploring temporal modeling with RNN, or transformers to extend context. We are working on a class-specific optimization to tune thresholds for stealthy classes. We plan to test in-sample models and invertial robustness. We are parsing operational deployment to validate transferability and latency in live systems. And we are investigating semi-supervised and online learning for improved learning efficiency in resource-constrained environments.